Welcome to Ask and Learn.
Hi, in the given problem, here this is the loop as shown in the figure. This is the metallic bar which is moving over the loop with a speed v, and the magnetic field in inward direction is B, entering into the plane of paper perpendicularly. Width of the loop means the length of this slide wire. Length of the slide wire, which is given as L. Now, in the first part of the problem, we have to find an expression for the force acting on this slide wire when it is moving towards right with a speed v at any instant. The expression for the force which will oppose the motion of this bar towards right as per Lenz's law. So for this, first of all, we will look for an expression for the EMF induced, which is a standard expression, and it is given by the product of B and V and L. This is the expression for EMF induced. Now, the current in this rod will be given by using Ohm's law. I is equal to EMF divided by the resistance. So, finally, the magnetic force acting on this bar will become B multiplied by I multiplied by length of this bar. So, it comes out to be B epsilon by R multiplied by length. So, this is B into BVL into L divided by R. So this force acting on this bar towards left in a direction opposite to the direction of motion will become B square VL square divided by resistance R. This is the expression of the force and the answer for the first part of the problem. Now, in the second part of the problem, we have to obtain an expression for the distance traveled by this rod as a function of time, because the force acting on this rod, the opposing force, will keep on changing with a change in this speed v. So the distance will also be given as a function of time. So to do this, we will equate this force with the laws of motion, Newton's second law of motion. So we can say this B square V, L square divided by R may be given as negative of mass into acceleration, if the acceleration is the if A is the acceleration in this bar. So the expression for this acceleration will come out to be minus B square V L square divided by M times of R. And we know acceleration may be given as the derivative of speed v with respect to time. So it can be given as dv by dt. So rearranging the terms here, we get 1 by v dv is equal to negative of b square L square divided by m times of r dt. So we can convert this small changes in speed and small changes in time in terms of the final speed and final time using integration. So if the speed is changing from initial v naught to final v, here it will become integration of 1 by v with respect to dv. And if the time is changing from initial 0 to any final t, here it will become v square L square divided by m times r as a constant will be taken out. the limits over time are from 0 to t, and this is just dt. So integration of 1 by v with respect to dv comes out to be natural logarithm of v over the limits from v naught to v. And here it will become b square l square mr t, having the limits of time from 0 to t. So putting these values of limits, we finally get the natural logarithm of v by v naught is equal to minus b square l square t divided by m times of r. Or converting this logarithmic form into exponential form, we get v by v naught is equal to e raised to the power minus b square l square t divided by m times of r. So finally, the expression for instantaneous speed in terms of the initial speed given to this bar v naught is v is equal to v naught e raised to the power minus b square l square t by m times of r, where m is the mass of the bar and r is its resistance. Now, we know speed may be given as the derivative of displacement. So we can convert this v in the form of derivative of x with respect to time. So dx by dt is equal to v naught e raised to the power minus b square l square t divided by m times of r. So here, if we integrate it, we can get, this is the integration of dx over the limit from initial displacement, which was 0 to final x, is equal to v naught e raised to the power minus b square l square t divided by mr over the limits of time from 0 to t and dt. So the expression for this x comes out to be v naught, being a constant, can be taken out, and the integration of this e to the power will remain same as e to the power minus b square l square t divided by mr. Now this function as a power of this e will be differentiated with respect to time, and we will get here this minus b square l square by m times of r, which will become, and here this will be having the limits of time from 0 to t. So this will become v naught times of minus m times of r divided by b square l square modulus e to the power minus b square l square t divided by m times of r, having the limits of time from 0 to t. Finally, when we put all these limits, we get an expression m r v naught divided by b square l square bracket 1 minus e to the power minus b square l square t divided by m times of r. Now, when the speed of the bar will become 0, means for v to be 0, we look in this expression. If we need the speed to be 0, clearly the time should be infinite. So if the time is infinite, then this expression for displacement will become mrv naught divided by b square l square multiplied by e raised to the power minus infinite, which will come out to be 0. So finally, this distance get a form of m r v naught divided by b square l square. This is the final answer for the displacement of the bar when its speed will finally reduce to 0. Thank you.